Hello everyone, I am Anish from EC department. In this lecture, I will be discussing about FIR filters. Before going directly into the FIR filters, let me throw you a small scenario. Suppose, let us say, Singh sir is playing guitar and I am playing keyboard. I am playing a C major scale C, D, E, F, G, A, B, and VP Singh sir is giving me the corresponding chords: C major chord, D major chord, E major chord, F major. Suppose I want to extract the frequencies in between F3 and F5. So as per our knowledge, till now we have discussed only IR, so we'll use a IR bandpass filter. That's fine. The other frequency components will get attenuated and only these components will be passed. That's fine. The amount of amplitude is fine. But what about the phase? Phase. Suppose I am playing E and sir is playing E major chord, but as IR filters are non-linear, the phase response is non-linear, so the timing of the corresponding frequencies will be changed. If I play E and the sir is playing E major, but due to the non-linear phase, I may hear the F major chord for the E key, and this will sound very odd. And similarly for F, sir plays F major, but due to the non-linear phase, I may hear E major or G major. So without going in depth, just a simple scenario where linear phase is important. So this is one case where linear phase is important. So now we want a filter to have a linear phase. So what is linear phase? In linear phase, the each frequency component will get delayed equally. And this raises the another question. Are all FIR filters linear? Pause the video and think for a while. The answer is no. FIR filters still they can be non-linear also. Because this linearity condition, it only depends upon the symmetry of the impulse response. If the impulse response is symmetry or anti-symmetry, based on that the phase is linear. And okay, that's fine. Now we have understand what is linear phase and what are FIR. So what is difference between IIR and FIR? So FIR are finite impulse response. They have finite impulse response. IIR, they have infinite impulse response. Like in IIR, due to the feedback, the filter response will be oscillating. If you take the impulse response of the IIR, the response will be oscillating. At infinite, the response will become 0. But if you take some finite interval, say 10,000 or 1 lakh or 10 lakhs, even in that interval, still there will be oscillations, but those will be not equal to 0. Like it will be very exponentially very less value. So that's the reason we are using FIR filters, where the impulse response will be finite, and basing on the symmetric or antisymmetric conditions, we'll be getting linear phase. If the impulse response is not symmetric, then we'll be getting a non-linear phase. So to get FIR filter, we have two methods. One is windowing method and one is frequency sampling. In this video, I will be explaining the windowing method. The linear phase, it mainly depends on the symmetric and antisymmetric conditions of the impulse response. So only if these conditions are satisfied, then the phase will be linear. Otherwise, the phase will be non-linear. Even though it is still a FIR, if it is not symmetric, we'll get a non-linear phase. Now, basing on the length and symmetric antisymmetric conditions, we have types of FIR. If the length is odd and H is symmetric, it's type 1. If length is even, H is symmetric, it's type 2. Similarly, if it is odd and antisymmetric and even and antisymmetric, we have type 3 and type 4. Okay, now we have understood what is linear phase and what are types of FIRs. So now how to start, how to get this FIR. Till now we have studied about IAR, right? Now we'll take impulse response of that IR, and then we'll apply a window. We will make the impulse response to be finite. So the reason we are applying window is we are making the infinite impulse response to finite. We will be taking only this part. This is known as a window. Okay, we have got a finite window. Now we can just apply the frequency. We can get the frequency response of that, and just plotting it gives FAR. But this is wrong, because the impulse response of IR filters, they are not symmetric. So that's the reason this approach is wrong. So instead what we will be doing is, we will be taking the ideal frequency response of each corresponding low pass, high pass, band pass, and band stop. So this is the reason why we are taking ideal frequency response, and we will proceed from this ideal frequency response instead of taking this IAR and then windowing the impulse response of the IAR and then getting the frequency of that. So the idea will be, first we'll take the corresponding frequency's ideal response, and then we will calculate its IFFT to get its impulse response. As this is ideal frequency response, the impulse response will be symmetric, and we will use the FFT shift for better visualization of the impulse response. Because if you don't use FFT shift, the same sync wave, if you take this is sync wave. If you use FFT shift, this will be the output. If you don't use the FFT shift, the output will be like this. Like half part will be here, half part will be here. So we use FFT shift for better visualization. And then we will multiply before multiplying with the window. We will decide the length of the window. If we take some 100 samples, then we will extract this corresponding 100 samples from this frequency response, sorry, from the impulse response. And we should keep in mind that while extracting the samples from the impulse response, we should take the symmetric thing. If the impulse response is like this, we should take the samples in such a way that these should be symmetric or anti-symmetric in order to get a linear response. So this is the very important thing. And then we'll multiply with the window, and the length of the extracted impulse response should be equal to the length of the window, and then we'll multiply it, and the rest is simple. We'll just calculate its frequency response by using FFT, and then we'll plot its magnitude and phase, and let's see whether it is linear or non-linear. So before going into that, let me just give you a brief on low pass, high pass, band pass, and band stop. If you consider the omega c, which is in between omega p and omega s. So what we'll be doing is, in the ideal case, till omega c it will pass, and after omega c it will strongly attenuate in the case of low pass. Till omega c, from 0 to omega c, it will stop the corresponding frequency components, and after the omega c it will pass. Similarly, in the band pass, till omega c it will stop, and in between omega c1 and omega c2 it will pass, and after omega c2 it will stop. And this is the reverse in case of band stop. Till omega c1 it will pass, after omega c1 and till omega c2 it will stop, and after omega c2 again it will pass. So you should understand this clearly before getting into the simulation part. And if there is some time delay in the time domain, if the sync wave is shifted instead of 0, if the sync wave is symmetric around alpha, it means it is delayed by alpha times. So if there is delay in the time domain, then it is exponential factor in the frequency domain. So that's what we can see here. So if you take alpha equal to 0, in the time domain, it is symmetric around 0. If you shift by some, if alpha is not 0, if you say some alpha value, which is not equal to 0, then the impulse response will be symmetric around this alpha. And here you need to be careful while extracting. You should center around alpha and you should extract this part in order to further multiply it with the window. Now coming to the simulation part, I have taken alpha equal to 0 for simplicity. So this line corresponds to the plotting of the ideal frequency response in the frequency domain. And then I have used the IIFT and then plotted the ideal response, ideal impulse response of the signal. Here you can see I have taken 2024 samples from minus pi to pi in the ideal. So in the ideal frequency response. So similarly in the ideal impulse response, that is in the time domain, I will be getting the same 2024 samples. And here you can see at x equal to some 1994, in the ideal case, the y is not 0, it is some small value. So that's what I discussed earlier. In the ideal case, the oscillations will be continuing till infinite time. At infinite, you will get the 0 uh, value. So now we got the ideal impulse response, and there are 2024 samples in this. And here I have defined the length of the window. I have taken 101. So I need to extract 101 samples from this. As alpha is 0, it is centered at 0 and symmetric around 0. So I'll be taking let us say 50 samples to the right side of the origin and 50 samples to the left side of the origin. So this code corresponds to the extracting of 50 samples after x-axis and after y-axis and 50 samples before y-axis. So this is the extracted ideal frequency response. You can see it is minus 50 to 50. And then this code corresponds to the window. I use the inbuilt function Hamming. So this produces the corresponding length 50 samples of window. And then next is we need to multiply this window with this extracted impulse response. And this code corresponds to that multiplication of the extracted impulse response with the windowed impulse. And here you can see this is now the finite impulse response. In the name itself there is a finite impulse response, and this is where by multiplying with the window we have made the impulse response to finite. So after multiplying with the window, now I have the impulse response in the time domain. So in order to get the frequency response, I am using the FFT, converting from time domain to frequency domain. So here I have done this FFT. So here you can see it is similar to the ideal frequency response, but the only thing which differs these both is there the impulse response is infinite. There the impulse response is infinite, and here the impulse response is finite. And coming to the phase, here I have plotted the phase of the FIR filter. So here you can see the phase is linear, but if the phase is linear, there should be straight line. But here I am getting some zigzag lines. So how this thing is linear? So basically, when I use the angle command, it just gives the corresponding angles in the minus pi to pi range. Like these are wrapped in the minus pi to pi range itself. If I use the unwrap command and try to unwrap these angles, then here you can clearly see that there is a straight line. The frequencies where the filter has allowed, that is in the low, that is less than omega c, there you can see uh, the phase is linear. So similarly, now to construct a high pass filter, we can use low pass filter to construct the high pass filter. If you see the ideal frequency response, it is allowing these frequencies and it is stopping this, right? What if you shift this? So this is the magnitude response of the low pass filter. Uh, you can see I have plotted from minus pi to pi. Here it is normalized, so it is minus 1 to 1. Here you can see below the omega c, it is allowing, and above omega c, it is highly attenuating. So this is low pass, right? What if you invert this? If you flip it by pi radians, what happens? This acts like a high pass. So that's what we'll be doing in order to get the high pass filter. It is one of the approach by which we can do it. So here I have taken same the low pass filter, and then I have calculated the IAFT, and then I have extracted the corresponding length, and uh, I have created the window. Here I have used the Kaiser window, and then I have multiplied with the window. Here, see, to flip the things in the frequency domain, in the time domain, I need to multiply with alternating minus 1. So this code corresponding this code here, this line corresponds to that flipping of pi radians in the digital domain. And after flipping, the rest is same. Again, you will use the FFT to calculate the re digital response and the magnitude. And here you can see, before it was like this, it was allowing. Now I have flipped pi radians, so now it is like this. So here it is allowing, and in between the low frequencies, it is highly attenuating. So this corresponds to the high pass filter. And if you see the phase, the same thing, because of the wrapping, you cannot see the, actually it is linear, but because of the wrapping, you can see there is some zigzags. If you use the unwrap command, then you can see it is linear. It is allowing the high frequencies. So at high frequencies, the phase is linear at this part and even at this part. Now the other method which we can do is, we can take the ideal frequency response of high pass filter itself, and then we can use the IIFT, and then extracting the corresponding samples and constructing the corresponding window, and then multiplying the window with the impulse response, and then calculating its frequency by FFT command, and then plotting its phase and magnitude. So here you can see this code corresponds to the ideal frequency response of the high pass. Here it is allowing, here it is pass band, and here it is stop band. Here I have taken alpha equal to 0. So there is it is centered around the alpha. If you take alpha equal to some 10 or 100, you need to be careful while extracting the impulse response from the time domain. Like you should take the samples. If the order is 50, if the order is say 50, you need to take 50 samples after alpha and 50 samples before alpha, and multiply that length with the window. So same, I have done IAFT, and then extracted the samples, constructed the window, multiplied with the window, and then used the FFT. And here you can see it is similar to the high pass. Before example, I have multiplied the impulse response alternatingly with minus 1, and here without multiplying with minus 1, I have taken the ideal response of the high pass filter itself, and then I have calculated step by step. And in the same manner, This is the windowed impulse response. This is the windowed impulse response, and this is the magnitude response. And if you see the phase, same, before unwrapping it is zigzag, and if you unwrap, see, at high frequencies it is linear again. So similarly for the band pass, you can construct the band pass using a low pass, or you can directly take the ideal response of the band pass and then you can calculate a IIFT and then extract the corresponding samples. If the alpha is not 0, then take the samples, say if the order is 10, the order is 100, then take 50 samples above alpha and 50 samples below the alpha and multiply with the impulse response, and the rest is same. So stop band, and this is pass band, and this line of code corresponds to plotting of this ideal frequency, corresponds to ideal band pass frequency response. And then I have used the IIFT and then extracted the corresponding samples and then constructed the window and then multiplied with the window and then used the FFT to plot the frequency response. So here you can see if you take omega C1, which is omega P1 plus omega S1 by 2, which lies in between omega P1 and omega S1. Similarly, omega C2 lies in between omega S2 and omega P2. If you observe, the frequencies in between these are getting passed with less attenuation, and the frequencies less than omega C1 and above omega C2, they're getting attenuated. So if you see the phase after unwrapping, in between omega C1 and omega C2, we are getting a linear phase. In the case of minus pi to 0, and even in 0 to pi, we are getting the linear phase in between omega C1 and omega C2. So similarly for band pass, we can design it using low pass, or we can directly proceed from the ideal band stop frequency response. So here in between omega C1 and omega C2, it is stop band, and above omega C2 it is pass band, and below omega C1 it is stop band. The rest is same. This line corresponds to the ideal frequency response of the band pass, and then calculating of IIFT, then extracting the samples which are centered around alpha in order to multiply with the window, and this corresponds to the construction of the window, and then here multiplying with the window and then plotting the frequency response of the filter. Here you can see in between omega C1 and omega C2 it is attenuating, and below omega C1 it is passing. So here you can see at exactly at omega C1 you can see some attenuation here, and exactly at omega C2 here you can see there is not that much attenuation. So by reducing or increasing the transition width, uh, you can adjust these values so that it will reach the ideal response. So if you see the phase, unwrapped phase, then it's a bandstop filter. So uh, the frequencies where it is highly attenuated, there you can see some zigzags, and other than that you can see there is a linearity. Here you can see there is a linear, and here it is linear, and again here it is linear. So this is construction of FR filters using a windowing method. If you find this video helpful, share with your friends, and if you are still seeing this video, it means you have exam tomorrow. All the best for your exam. Bye bye.